My project focused on determining the effect of abrasion on the optical properties and strength of float glass. Float glass is a type of glass manufactured through the float process. The float process involves flowing molten silica over a bed of molten tin. This allows for the creation and production of large quantities of uniformly thick glass at relatively cheap cost. This has made it a very practical alternative in the manufacturing and production of transparent armor systems used by the military. Float glass is commonly used as the strike face of transparent armor systems because, as I said, it's readily available and cheap, but can be made in large quantities. Float glass also maintains some very useful properties. Float glass is rather strong compared to other ceramics and rather hard, which means it's resistant to scratching. This has made it a very useful tool as a strike face in transparent armor system because it'll be used as the strike face that ballistics contact. Currently, as the strike face, float glass is exposed to a lot of environmental conditions, such as in the field or the modern battlefield. Sandstorms and contact damage may come from flying debris or dust. Now, when glass is contacted with this debris, its strength is affected. Now, how much, we don't really know. At the same time, optical properties are changing. In the long run, the conventional method for determining strength is ballistics testing. Now, ballistics testing involves destroying the plate in the process due to the fact that we're firing a projectile at it. And the problem is, your results may reveal that the float glass was perfectly fine to begin with and didn't need to be destroyed. However, ballistics testing is a destructive methodology. My goal is to develop a non-destructive method for determining the strength of float glass, and we will do that by using optical properties. We found from the beginning that as we induce flaws in the glass, the flaw is not only changing the strength, but also it's affecting how light passes through the glass and therefore affecting optical properties. The optical property that we chose to focus on is haze. Now, we simulated contact damage through abrasion. The abrasion was done with a number 12 grit aluminum zirconia, which is similar to pea gravel. We used this fabricated jig to hold the glass plate and allow us to introduce the abrasive material on the plate surface. The jig would then be laterally oscillated using a Tabor tester for a set duration. As you can see here, the durations varied from 0 to 1200 lateral cycles. Now, as you can see from our results, as abrasion increased, you can see that in both glass types, the haze was increasing because as flaw density, the number of flaws on the surface increased, and you're going from a linear glass surface to a non-linear jagged surface, light is being transmitted at a diffuse angle, causing haze to increase. At the same time, as flaw density increases, it's reaching a critical flaw density or critical flaw width and depth, causing the glass plate to fracture. As you can see here, Borofloat is much harder than SLS, which explains why it's resistant to initial damage, and it's maintaining somewhat of a baseline strength until between 150 and 300 cycles. At that point in time, when a critical flaw density is reached, the glass plate fails. In SLS, due to its soft nature, it's failing much sooner at lower abrasion levels. At the same time, we recognize that at the moment that the glass fails and you reach this drop-off, if we're able to isolate the value of haze that corresponds with that drop-off, we can use that haze value as a quality control standard for manufacturing purposes. Therefore, the manufacturer can be alerted to that if any of their glass that they're manufacturing has a haze value registered at that value or above, there's statistical reason to believe that the strength has been degraded a significant amount and it should be taken out of circulation. Now, for purposes of from a military standpoint, float glass used in transparent armor systems can be controlled by the soldier or the warfighter in the field. If they have a handheld haze guard, they can measure the average haze of a transparent armor system, whether that be a windshield or a side window, on the battlefield or in the field, away from a workshop or lab. This would allow them to preemptively or proactively repair or replace their transparent armor system and confidently operate while feeling safe. This not only saves the taxpayer money, but it also protects the modern warfighter in the long run.